So, all right, so what we're going for is a library of stuff for doing environmental cleanup, healing the planet, not just one product. What we're going to do here is focus on a schedule for a product, and what you do then is just hit repeat, okay, and do it again. So this is where we are right now. So right now, our basic technology was backed by 30 million in private equity. Yes, and plus, very grateful for SBIR grants from NSF and Department of Energy. Department of Energy, thank you, David Forrest, enabled us to bring up the prototype manufacturing line for the key component, nanomembrane manufacturing, which now means that where we stand is the ability to bring up full-scale manufacturing. So, where we're heading for is, we've got 65 million of upfront cash coming in the door, which will let us build out our dual manufacturing lines for our first 2 sets of water-related products. And what's happening is it's customer validation going to customers who bring in their technical experts, who kick our tires, and then they go back to the company and say, you know, something like this could solve our problems. So this is doing pretty well. We have major contracts and pilot programs that have been requested across multiple industries. And what is it? We're solving their problems and saving them money. In the process, major environmental benefits. So we're not selling the environmental benefits, although they recognize them pretty quickly. We're solving their problems, we're saving them money. Okay. This is what we've done in terms of status and schedule. What we've done, we've already designed the first products, we've already designed stuff. And the basic notion here becomes that what we will do is you intervene, you go back to the design board, you bring up your computational chemistry. Thank you, Caltech, thank you. Bring up your computational chemistry and design your new product, build and test, and drop it into the manufacturing system. So what we're looking at, we're 3 years, by the way, from now to bringing up our full-scale plant. But if you were to start designing a brand new product today, you could slot it into that 3-year time schedule. So what's the deal? Doing a new pour or a new building block for a new product conservatively is going to run you a year and $8 million for your new product. If things go well and it turns out to be an easy build, an easy design and build, okay, it's going to be less than $8 million, but I'm not getting Marty to commit to what that's going to be because he wants the $8 million for other stuff. But anyways, so what's the schedule? So it looks like this, okay? So what you're in is a design phase. You then test the pour that you've built. You may cycle on this, okay? You may find that what you've built, you're not happy with it, okay? And so you may iterate that a few times, and then what you do is, once you've got pours that you're happy with, you scale them up, you begin testing them in a full membrane, and then test the membrane, drop it into your breadboard, and off you go to production. What we're counting on, by the way, is that when we're bringing up the gas pours, okay, because that's the next thing that we've done water pours, now we're going to do gas pours. So what we're counting on is that we can go back to, remember the molecular toolkit? You can go back to your toolkit and reach in there and pull out components that you've already developed for water. So pull out substrates you've already developed for water. Pull out surface chemistries that you already developed in order to have non-fouling in your water applications and deploy them now for your gas filtration products. So that certainly saves time and energy. So basically what you're looking at here is a development cycle where it's rinse and repeat. Okay? What do you want to build? Do it some more. So those are your milestones. Did you build what you thought you were going to build? And what does it look like in terms of costs? Well, so it's like this. Sorry? Well, this is great. Unbelievable. So, okay, so what's the deal here? Okay, this is the kind of team that you're going to need to put on it. You got to go back to computational chemistry, okay, as you keep working in new areas. Expand your software suite. Take what you've learned about how to build these constructs and do it again. Cycle it, which is what we do. Take the knowledge from building the pores, cycle it back into the software, so you keep understanding reality better and better as you go along. And that's the deal. Okay? Question? Make them easy.
What are your questions? Who'd like to start? June.
So you talked a lot about processes and your design cycle and your platform. I think I was still not very clear what your product was and go-to-market strategy with the product, or are you a service?
Oh, okay. So I'm assuming that this explanation was based on the assumption that you were here and heard the earlier discussions. No, okay, here's the deal. So what we are is a research, design, and manufacturing shop, okay? We then hand off product to a licensee who may be selling a product or delivering a service, okay, or other models as they see fit. We are staying focused on moving that R&D forward, okay? So what we're doing is we build. At the moment, the product that we build is a 1 atomic layer thick, atomically precise membrane that does filtration, separation for water purification and desalination. 2 separate product lines. It's a different paradigm than what's currently out there. So instead of it being, what do you want to remove from your water? So what's noxious that's in there that you want to take out? Instead, we reverse the paradigm. We do a renal paradigm. The kidney's paradigm is, I keep what's vital to life, I throw everything else out. If there's a new contaminant that I don't know about because I've never experienced before, you check the short list. Is it on my short vital to life list? No, out it goes. So that's basically what people want. What people want is product water. The way it's done with existing technologies, however, is what we'll call stacked solutions. You go, what's in my water that I know about that I don't want? Oh, I'm Central Valley, California, I have boron in my water, I need to take that out. Oh, I have nitrate in my water, I need to take that out. Oh, the EPA has just told me I now have to check for arsenic, because now that's regulated. Oh, look, I've got arsenic in my water, now I have to take the arsenic out. Oh, wait, hexavalent chromium, now I gotta add another system on to take hexavalent chromium out. Is this an ideal solution? No, what you want is to specify your product water. What I want is, I want the water that my kidney could not reclaim and that I lost through respiration or perspiration. So I want a kidney out there in the world that gives me kidney quality product water. I want the stuff that's vital to life, and I want nothing else, toxic spills, etc. So it's a different paradigm. And what it does is it means that you're at 1 atomic layer thick, the lowest energy possible, with high specificity. So that's the holy grail of separation science. And it makes things cheap. It means that you can have distributed systems. You don't need the cost. You don't need a central plant. You can do this at your home, on your tabletop, at a distributed wellhead site. And now you don't have transportation energy and you don't have transportation losses. Okay?
Go ahead. Well, so the success of this really depends on your ability to identify the right specific chemicals to carry this out. And how successfully are you able to go from computational chemistry to the real world in doing this?
Fantastically successful. It has been a major pain in the neck, and we have been told at various steps along the line that what we were attempting to do was impossible. Unfortunately, we were told this after we had done it, so that had to be amended to, well, it's just very, very hard. And we can do unprecedented separations, things that no one's ever done before. No human created material has ever done.
So I didn't see any, what state of the art? What are the metrics that you have that you're going to work against? I didn't see any of that, and I have a whole bunch of other questions, but let's just leave it at that. What are the metrics? Why is this better than state of the art?
Okay, so let's see, we've done some earlier inclusion. I would have loved to, I've got data slides to show you. Reduces energy requirements for purification by up to 99%, for desalination by 66%, eliminates rejection ratios found in state-of-the-art polymeric membranes. Your exclusion for an unwanted contaminant is 100%. So the stuff you want comes through, stuff you don't want that wrecks your product water definition, the exclusion is complete. We have data to show this. Can anybody else do this? No, they cannot. Costs reduced in state-of-the-art polymeric membranes. Your CapEx, OpEx, total cost of doing business to the bottom line of the business. It's cut by, like, on a minimum 50% for a retrofit, 28% for small to medium retrofit, going up to about 50%, and then more for greenfield construction.
It's like hard to understand what somebody investing in this company would be owning. It sounds like they'd own a percentage of a consultancy, which is like licensing out IP. Is that right?
No. Okay, so the way we've done this is we have followed the corrected version of a Thermo Fisher model, where what's happening is an exclusive right, worldwide right, is granted to a broad swath of the market. So in this case, when you're talking about water, you're talking about the right to all commercial water applications. So this becomes like Intel Inside, where Intel ships you the chips, and you're making smartphones and you're making laptops, etc., based on the chips, okay? Or you're selling computation services or telecom services based on the chips.
You guys are making the physical chips?
So we're making the physical membranes, okay? We manufacture them, and then, so somebody who's got, so Agua Via, for example, has exclusive rights to the water domain for commercial water. So in other words, not biological water, not water in your body, okay, and not water vapor. So you have to make it as a technical set of distinctions. But in terms of desalination, wastewater remediation, water for drinking, environmental cleanup, industrial processing of water, it's theirs.
All right, thank you very much. All right, thank you, Gayle. Thank you for this presentation. Thanks for the questions.